Since we left off yesterday talking about how a unit is the actual unit of measure, whereas dimension, we're talking about things like it being either length or mass or time. That is your dimension. The unit is what you're actually measuring it in, like grams or kilograms or meters or seconds. Okay. So actually, I think we can go past that. Don't worry about copying this down. That's not that important. Yeah, we talked about this yesterday. I didn't get to. And we said yesterday you need to make sure you know prefixes mega to micro. And that table that you just saw is in your textbook. I don't know what page it's on, but it's in there. We talked about that yesterday, and that.
Where's that noise?
I don't know. I know. I thought for a minute I was going crazy.
Oh, is it that phone? What is the red light mean?
It means I have a missed call, but
Maybe it's the Bible.
every time I've called up there to see what my missed call was, she's like, "I didn't call you." So today we're going to talk about. We said yesterday. Let's go back to this one. We said yesterday that in physics, when we do a math problem, because math is going to be all through here, that our dimensions have to be consistent. So if in an equation, both sides of the equation when we're done have to have the same units. You can't just stuff in numbers and work out the equation like you do math. You've got to have a unit that goes with it, and your units have to be consistent. Okay? So if we have this formula, for example, it's a formula for determining your final displacement or your final distance away from something. So final distance is equal to the initial distance or initially where you started plus your velocity times your time. When you put all the units in there, they have to wind up coming out to be the same unit all the way across. So VF is length, VI is length, because those are both distances. V is length divided by time, that's our velocity, and then time, of course, is time. So when we do that, time cancels because you got time on the top, time on the bottom, so they cancel out. And that means we have length all the way across, which is what is supposed to happen. So if you're doing a calculation and that doesn't happen, then you have used the wrong formula. Okay? So you got to have them all come out to be the same dimension. Okay? And that's from yesterday. Okay? So today we're going to look at changing units. This type of calculation, one written in terms of dimension, refers to as dimensional analysis. So when we talk about changing units, changing back and forth, that's what we call dimensional analysis, where we can change from one unit into a different unit. Okay? So let's get that out here. Calculation written in terms of dimensions is what we call dimensional analysis. Okay? A lot of times we have to convert from a non-SI unit to an SI unit. Well, what in the world is an SI unit? SI unit just means the metric system. It's the system we use in science. We don't use feet and inches and pounds in science. We use the metric system. So sometimes you're going to have to convert between those two. That takes dimensional analysis. So here's an example. So if you want to jot this example down, you'd like to convert 316 feet to its equivalent in meters. So we look for a conversion factor. You'll find that 1 meter is approximately 3.28 feet. And then we just set up our dimensional analysis. So when you make the little ratio, because that's what this is, Your dimensional analysis is we would make a ratio equal to 1. So 1 meter is 3.28 feet. So we can set up that ratio, and that's the same thing as multiplying by 1. So here's our railroad tracks is what we called it. They may look a little bit different, but 316 feet, and we put feet on the bottom. Why do we put feet on the bottom? So they cancel out. So we put what we want to cancel out on the bottom of our railroad track, what we want to get on the top. So we know that 1 meter is 3.28 feet. Oh, I'm sorry, I did not mean to clear that. Sorry. I will write that over. There we go. Feet. 3.28 feet over 1 meter. Feet cancel out, so we're just going to take 316 and we're going to divide by 3.28. That's it. That's all there is to it. Big deal. Okay? So if we have our calculator and we divide that out, we get 96.3 meters. All right, so I'm going to stop right here and jump ahead just a minute and talk about significant figures. We mentioned significant figures in chemistry last year, but we didn't focus on them a whole lot. In physics, we tend to focus on them a lot more. Okay? We just focus on them a little bit more. So significant figures says that your answer cannot be more accurate than the measurements you took to start with. Okay? So we measured 316, we measured that out to the ones place, to feet. All right? So how many significant figures are in the number 316? 3. The 3, the 1, and the 6. Okay? We do not really count conversions when we're doing these. Well, actually, I take that back. That's wrong. That's incorrect. If it's a conversion between meters and feet, between SI units and non-SI units, we do need to count significant figures in that measurement because that's an estimate. There are not exactly 3.28 feet in a meter. It's just an estimate. So how many significant figures would be in 3.28? 3. So how many significant figures should be in my answer? 3. Which is why we rounded to 96.3. You do it on your calculator, you get 96.34146341. Okay? But to keep it at 3 significant figures, we round it to 3. Okay, I'm going to open this door to see if it's in here or out there. Some weird thing on my phone. Okay, so that's dimensional analysis. Any questions on that so far? Has everybody got that written down? Okay.